between two vectors. That is called an inner product. So if we put an additional structure on the vector space by defining an appropriate inner product, then that is called an inner product space. Just like by defining a norm, we get a normed vector space. By defining an inner product, we get an inner product space. Now, if completeness is there for the inner product space, then that space is called a Hilbert space. So a complete inner product space is called a Hilbert space. So when we talk about Hilbert space in quantum mechanics, every solution space of Schrödinger equation that we have has all these properties. You have it's a vector space, you can define an inner product, and completeness is assured. A complete inner product space is called a Hilbert space. So in that, first today we talked about only vector spaces. Tomorrow we will talk about inner product spaces, completeness, and tomorrow forenoon I think we will come up with Hilbert spaces and complete our discussion on vector spaces and Hilbert spaces. And tomorrow afternoon onwards we will talk about linear transformations, operators, and other parts of the Hilbert algebra. So just before I leave, I want to define two more. We have seen if we have a bigger vector space, how to get lower dimensional vector spaces we have talked about. Now if I have two vector spaces, how to construct a bigger vector space? There are two ways of constructing that. One is called direct sum of two vector spaces. The direct sum of two vector space is by construction of vector space. I have one vector space, I have another vector space. I make it a direct sum of two vector space. It's always a vector space. Okay, so let us say that I have a vector space V1 which is m dimensional. What does it mean? It means I have got elements x1, x2, etc., xn, such that x1 to xm are in the V. Now let us consider V2, which is an n-dimensional vector space. That means I have from y1, y2, etc., yn, such that y1 to yn also in F. Now we can define V and we write it like this: V direct sum V2. Okay, V direct sum V2 is a vector space. It is defined as Z1, Z2, etc., Zm plus n, such that Z1 to Zm plus n is V. You can do a direct sum of two spaces if they both define on the same field. They both should be on reals or they both should be on complex numbers and so on. So what is the dimension of V? Dimension of V is equal to m plus n. It is just appending. First m are from that, second n are from this. So Z1 to Zm will be xn. Zm plus 1 to Zn m plus n will be yn, like that. So it's just an appending. So if I have one line, x-axis is a vector space, one-dimensional vector space, y-axis is a one-dimensional vector space. Direct sum of these two vector spaces is the plane. Geometrically, that is what it is. XY plane and then z-axis. Direct sum of these two will be the entire space and so on. So this is called direct sum of two vector spaces. This is one way of constructing, having some lower dimensional vector space to higher dimensional vector space. Now we talk about direct product. Direct product of say these two are new vector spaces. Direct product is defined as V1 direct product V2. Please look at this carefully. This one is x1 times all the y1, yn, x2 times all the yn, and so on, xm times all the yn. So how many elements will be there? M times n, correct? So you can call this as Z1, Z2, etc. Z times M times n in the field. So dimension of direct product is M times n. To give you a familiar example, if you consider two spin-half particles, you might recall from addition of angular momentum theory. If you take two spin-half particles, each particle will have a two-dimensional vector space. So when you consider both particles together, it will be 2 into 2, 4-dimensional vector space. Okay? But when you do, so you know 4-dimensional vector space is the vector space of two particles. But then when you switch on something like spin-orbit interaction or some kind of a spin-spin interaction, then you know you will visualize this 4-dimensional vector space as 3 plus 1. That means a 3-dimensional subspace, direct sum, 1-dimensional subspace. That is a singlet and a triplet. A triplet is a 3-dimensional subspace of the 4-dimensional vector space. Singlet is a 1-dimensional subspace of the 4-dimensional space. So basically, one basis element is related to other basis element using Clebsch-Gordan coefficients. So this Clebsch-Gordan problem is essentially converting a direct product space in terms of the direct sum space. So that is essentially the mathematics that we do with Clebsch-Gordan problem. 2 cross